Hello, everyone. We are happy today to host Sebastian Hörl for this seminar at SystemX. So Sebastian is a senior researcher at IRT SystemX, and he is also an invited researcher at the Gretia Lab of Université Gustave Eiffel. Sebastian obtained his PhD in 2020 from ETH Zurich and his HDR, his habilitation in 2025 from Université Paris-Est. His research interests revolve around the replicable use of open data and software in transport planning and applied large-scale agent-based transport simulation. And Sebastian animates a research community around the open source framework eqasim. I hope Sebastian pronounced its name correctly, eqasim. Yeah. eqasim for reproducible population synthesis. And he will talk to us today about synthetic populations and agent-based transport simulation, replicability and application cases in France. So a very nice topic, and yeah, happy to receive you, Sebastian, and the floor is yours. Thank you.
Yeah, okay, thank you for the introduction. So, yeah, you already heard the title. We're going to talk about synthetic populations and agent-based transport simulation. And usually I like to start these kind of presentations a bit with a wider perspective. So what we see here is basically a street in 1900, somewhere in the US. And there we see that there's a lot of things that are going on the street. There are some vehicles, there are a lot of people interacting. So basically this is a lively place where a lot of it serves for a lot of purposes. And then in most cases, this has been transformed into something like this today, where we move tons of metal into the cities in the morning and tons of metal out of the city. All of these vehicles, they come with a spatial footprint. They come with emissions that they cause. We see that there are certain unwanted effects like congestion in the network. And the question that we can ask ourselves is this the ideal system, the ideal transport system that we can imagine? And in many aspects, probably not. In many aspects, however, it's better than our system in 1900. But we can ask the question at every point from 1900 to today, we could have made different decisions, like putting more collective transport or putting in place different network topologies to avoid congestion and so on. So at each point, we could have made a decision. And the question is, didn't we maybe have the right planning and prediction tools to find out what would be the better state in the future? And today, we're in a similar situation because there's still a lot of new technologies and a lot of new things arriving. So there's like delivery robots. There is autonomous taxis that are supposed to drive around in the city. There's like intelligent, smart infrastructure. People are talking about urban air mobility, where the taxis will fly in the air. So there's a lot of things that are upcoming still. And the question each time is how should we design our policies, our regulations, so that we actually get the benefits from all of this and we don't actually make the system worse than it is currently right now. And this is basically the idea behind transport planning. So we want to look into policies, we want to look into technologies and how we can optimize the system that exists. And this topic of transport modeling or transport planning exists already for a while. So in the 70s, people have started actually modeling transport systems. And there's these so-called macroscopic models that are still mostly the standard today. So what you do is you look at large zones, like for instance, here we see all the municipalities, the commune in the Île-de-France region with Paris in the middle. And then what you look at are the large flows going from one zone to another. So for instance, how many people go from one arrondissement in Paris to another one? How many people go from Palaiseau to Paris and so on? So we look at these large movements of people for the commuting flows in the morning or in the evening. And these models, they work really well if we want to analyze, for instance, where do we have capacity problems, where do we need to add more highway lines, where do we need to add more metro lines. And these were basically the questions that were asked for a long time to these models. And then the answer was, okay, here or there, we need to add more infrastructure. But today we are at the point where we have already a lot of infrastructure, so there isn't even much more space to build new. And also maybe we don't want to because of ecological reasons. What we try to do instead is to use the infrastructure that already exists in a more efficient way. So for instance, if we look at the service like Uber or other on-demand mobility services, they try to know where are all the people that want to travel and where are all the drivers, all the vehicles, and then we try to make a really fine-grained, intelligent match. And by this, we use all the digital numeric infrastructure that we have available everywhere and at any time today to basically make more intelligent decisions. But this we cannot represent with these classic macroscopic models, because we really want to look into the fine-grained dynamics of the demand, so of the people who want to travel, and the supply, so of the transport systems that exists. And for this, we need agent-based models, or for this we have started people have started looking into agent-based models. These models, our goal is to really represent all the people who want to travel in the system as individual entities. So for instance, one person here with social demographic attributes has an individual activity chain with things that this person wants to do. And these activities, they are connected by the trips. So basically we look into this activity-based concept where we say that all the movements that the population is doing are basically caused because the people want to do certain activities, like going to school, going to the restaurant, and so on. And in these simulations, we really simulate these people on a very dense time frame, like for instance, second by second, to really understand then how are they individually interacting over the whole day. So also here, a difference to these macroscopic models. We don't only look at one peak hour flow situation, but we really look into the movements over the whole day. So the question here is how to set up such simulations. And this is basically my main research question and research question that we treat a lot at SystemX. But there's also the question how to do this in a replicable way so that if I do a simulation, somebody else can do the same situation and with reproducible results. So if I derive certain results from these models, can somebody else exactly reproduce the same outcomes? So I think at SystemX, most of the people already met me, but in case somebody doesn't know, here just a small overview where and how I do this research. So as Faisal said, I already started with this at ETH Zurich, which is a major developer of such simulations. And then since 2020, I'm at SystemX and invited researcher at Cretia, where I did the HDR. So basically, this is also the basis for this talk here. So this is basically a summary of these slides that I showed to get my habilitation. So this is more like of a high-level talk that shows all these topics that we are working on to give you an overview of these activities at SystemX. And basically, this talk draws from a lot of different projects. So there have been at least 5 European projects at SystemX that all worked on topics related to this, but also a couple of industry and academic collaborations like with TU Munich and Volkswagen and SNCF. So from all of these different activities, we draw individual little components to set up these simulations in the end. So we can dive a bit more into detail what we actually need to set up such simulations. And there's 3 main topics that we look at, and these are synthetic populations, then the actual simulations and the use cases. And we start looking into this topic of synthetic populations. So as mentioned already, in our simulations, we really want to represent the daily mobility of our population, of a territory in detail. So we have individual persons, they have activities, and they move between these activities. And basically, for instance, for the Ile-de-France region, we will want to generate 12 million of those individual agents with their activity chains. And then in total, this should all be representative of what happens in reality. So our agents should have similar social demographic attributes. Our agents, they should have similar structures of the activity chains. So we try to really generate something that reflects the mobility of the whole population. And for this, we have set up a framework that we can basically look at step by step now to see how we generate this synthetic population. So the first step here is to generate households and persons. And for this, we can use a data set in France, which is the French population census. It's structured in this way, where we have individual households with an ID. Then there's individual persons with an ID. They have a home zone. So for instance, here the 13th arrondissement in Paris, they have an age, they have a gender, and they are weighted. So in this survey, we have about 30% of the French population. So to kind of scale it up, the statistical office ainsi provides certain weights that we can then use to just duplicate the households. And then, for instance, for the 13th arrondissement, we will generate, for instance, 3.2 on average people of this specific type here. And for this, we use truncated replicate sample, which basically means we will generate 3 households with these characteristics for sure, and one more with a probability of 20%, for instance. And this is then how we generate all the households and persons, and we already know where they live by municipality. In the next step, then, we use more data sets, which is the French building database, which contains all the buildings in France with their geometric footprint. And we have an address database, which basically gives us all the entrances to these buildings with the individual addresses and so on. So this address database is called a BAN, base d'adresse nationale, is, for instance, used when you order something online and you start typing your address, and then it's doing autocomplete on the website. And usually what is behind this comes from this BAN data set, because this is just a huge database with all the addresses that exist in France, and then with a geographic coordinate. So what we do with these data sets is, once that we know where these people live, in which municipality, is that we simply, inside of this municipality, we look for all the buildings. And for all these buildings, we also have in these data sets the number of dwellings, so the number of apartments or flats and so on. And then based on this number, we sample a certain building. So for instance, a large tower then will be sampled a lot more frequently than an individual house. And this is basically how, for each of our generated persons, we generate a home location. Once we have the home location, we can look into work. For this, there is a French work commuting matrix that comes with the census data set. So if we know the municipality where somebody is living, this is just a huge matrix that gives us the probability that this person is working in any other municipality in France. And of course, then closer municipalities are more probable than others. So basically, using this data, we can sample a work municipality, and we can attach this to our agent. And this is still quite coarse, so this is not as detailed as we want to, as we would like to have it. So what we use is Sirene. So Sirene is the database of all the facilities and enterprises in France. They come with the coordinates and with the number of employees. So basically, in each of these destination work municipalities, we sample a workplace based on the number of employees in every workplace. And this is also then how large workplaces get a lot of our synthetic people, and smaller workplaces, not so many. There's a similar approach for education, because we have a French education commuting matrix. So again, for each home municipality, we know what is the probability to go to school in any other municipality. And then there's something that is called the base permanente d'équipement, the l'INSEE. And in this data set, we have all the restaurants, all the cinemas, but also all the schools that exist in France. And we use this to sample schools and universities for the people dependent on their destination municipality. So at this point, we know the home location of the people, we know work location, and we know the education location if it's relevant to these people. But what we don't know yet is what they want to do during the day. And for this, we use something that is called a household travel survey. So a household travel survey is a process where somebody will call you and then they will ask you for a reference day. So what did you do in the morning? When did you leave home? Okay, so what was your next activity? Okay, at 8:30 you went to work until 5. And then basically they ask you about your whole day and you tell them everything what you did during this day. And this will be just registered in a data set. So for instance, for Île-de-France, there is the Enquête Globale de Transport, which has this data for 30,000 people. And then we can use this data set to actually sample activity chains, because we have exactly these chains that we want to add to the synthetic persons that we have generated. We find them in this data set. And what we do is that we take these individual persons, they have certain attributes, for instance, their gender, their age. In practice, we have many more matching attributes. But basically, based on them, we search in this survey data set people that are similar. So for instance, here for this person, we have a certain age range, we have a certain gender, and we search for similar people, and we find their activity chains here. And also in this data set, they come with a certain weight, so we can sample these activity chains, attach them to our agents, and quite easily we have the structure of what they are doing during the day. So this is quite a simple approach. There's many others that use deep learning, that use Bayesian networks to generate these activity sequences. But this is quite a robust and easy to explain approach, and it is kind of our baseline, and it's still most used in most of our use cases. So the last thing that is missing here is then, because is the location of these secondary activities. So we call primary activities home, education, and work. And then there's others, like going to the restaurant, going to the cinema, which for which we don't have yet the coordinates in our chain. And for this, we have a specific approach that we call secondary activity location assignment. This is a paper that we have published in 2021, and it basically is a process to use again this base permanente d'équipement to find all the restaurants, the cinemas, the museums, etc., and then find viable locations for all of these secondary locations. So, and then we have generated our synthetic population. So how does this actually look like in practice? So basically this is 3 tables. One table with the households. They have, for instance, an income, the number of cars, and other attributes. One table of persons, also with social demographic attributes. And we have a table of activities. So for instance, here for one person, we have the activity sequence. When do these activities start? When do they end? What type do they have? And what is the location in coordinates? And already with this data set, we can do quite a lot of things. So for instance, we can make a plot of all the places of residence of the people living around Paris. Or we make a plot, since we know the home location and the work location, of all the commuting relations of the population. So this is one example for Nantes. Or this is for Lyon now. We look at different times during the day, so at 8, 12, or 6 in the evening, where are all the people that are currently performing a work activity. So with our activities data frame here, with our table, we can do this quite easily. And the big advantage here is that we do all this analysis on the same data set. So we don't need to merge and join and clean and combine all these different raw data sets that we just saw, but we have already fused all of this into a synthetic population, and we can do all this analysis basically from scratch with our synthetic population. Of course, we validate all of this. So we can, for instance, compare the distribution of age classes in our synthetic population in gray with the census data set. We can also compare the social professional category. So are these people workers or intermediate professions, or like cadre? So all of these things, if they exist in the census, we can compare with our synthetic population. We can also compare the activity chains. So for instance, what we see here is, for instance, homework, home, what this person has been doing during the day. Home means that the person just stayed at home. Then we have home shopping, home education, home. And each time we see how often certain persons do this do this activity chain in the population. And here we look at men between 18 and 40 years and women between 18 and 40 years. And what we see, for instance, or what we see first is that our distribution, synthetic distribution here follows not exactly, but quite closely the distribution that we see in the household travel survey. But we see also, for instance, that for this this activity chain that most of the people do, homework, home, we have less women doing this activity chain. And what we observe is, for instance, that the distribution here for women in the synthetic data and in the real census, in the real household travel survey data is longer. So it's a longer distribution. And this is a phenomenon from sociology, for instance, that still, because there's still a lot of women who take care of the kids, do all these trips to the creche, the trips to the kindergarten and so on. They tend to have more complex activity chains than men, so chains that are longer. This is why we have a longer tail distribution here. And we see this in the survey data, but also in our synthetic data. So we actually represent, for instance, this sociological phenomenon in our synthetic population. Which means that if we do a simulation with this population later on, also we can figure out, if we implement a certain transport policy, what are the user groups that will be impacted in which way by this policy, and different people, different population strata will be impacted differently than others. So is it easy to generate such a synthetic population? Yes, because all these data sets that I introduced, all these raw data sets, they are open data. So you can go on this website of ainsi, of IGN, and just download them and do whatever you want with them. Also, the whole process that I just described is open source. It's on GitHub, and it's called eqasim. And basically, making this open source using only open data makes this whole process replicable, and the synthetic populations reproducible. So this is something that we published, and it's still quite a highly cited paper from 2021, because it's kind of the first one that actually describes how such a synthetic population can be described in a fully replicable way. And most of the people still don't do this, but this paper is also cited a lot. If some people, they set up simulations, but they cannot really explain where did they get the data from, how did they generate their synthetic populations, but at least they cite us and say, well, in theory, it's possible to do this in a completely transparent way. And I think this way we still have already pushed a bit the baseline. So we kind of encourage people to at least think about making all of this replicable, because otherwise nothing else that they do on the basis of the synthetic populations will be replicable as well. Since this is an open source framework, there's a lot of reuses. There's a couple of main contributors like Telae and Université Gustave Eiffel, ETH Zurich. But it has been applied in, I showed the example for Île-de-France, but for many other cities in France, because all these data sets, they are available anywhere in France. So you can easily apply this, and this is happening by a lot of different research labs, academic institutions and companies in France. And we will look at a couple of use cases from them in the end. So we also have an annual workshop for eqasim. So we had 60 participants at SystemX in December. And we will do this again this year. There's a Mattermost channel for the people who are active in this community in France. We also have a Discord server. This is all on the eqasim website. And we have a monthly exchange where we discuss a bit what are the open pull requests on GitHub, who will do what, and so on. So this is a dynamic that this is quite nice, that has started recently, that we really talk about all the code changes and then advance together as a community. There's also a white paper that describes a bit the whole approach. If you're interested and you don't want to read too much of things, there's like a 6-page white paper that I have linked here in French that describes a bit the whole approach, the next steps, and so on, that we have written together with Telae and Gustave Eiffel. So, but we don't stop at Île-de-France. So, for instance, we also have transposed this whole pipeline to other cases. So the exactly same pipeline exists for Sao Paulo, because surprisingly there, all the open data that is available in France is also accessible to everybody. We have adapted this to California, and there is a not yet fully as open released version for the whole country of Switzerland. And I show you some recent results, how we want to even further flexibilize the system. So at SystemX, we had a PhD student, Tiag, who basically spent some time in Cairo during his PhD. And he wanted to generate a synthetic population for Cairo. And it's a completely different context, because there's a lot of data. Well, there is not a lot of data. They really go into the pedestrian zones, do surveys to get at least a bit of data. So it's a completely different situation. And what we did is to take the few data that we have in Cairo, and we tried to fit it into this French pipeline that already works really well. And this gave us an idea to further standardize this process. And this is now something that is really also online and usable. We kind of applied this whole idea to Bavaria in a recent project with TU Munich. So basically, you can imagine that we have this pipeline here in the middle, which are basically our processing steps for France. And then into each step, there's a certain data set, like the census data, the buildings database, that goes into these steps. They're transformed in a certain way. And then at the end, we have our synthetic population. Now, the problem is that in France, we have a lot of data, so we can do this. In Germany, it's kind of the opposite. There's not a lot of data. If at all, there's kind of marginal data. So we know the distribution of age, we know the distribution of employment, things like this. But we never have really individual observations of people, anonymized or not. So this basically doesn't exist. So what we can do there is to use this marginal data that we have, apply some additional generative modeling approaches, and then try to generate a data set that looks exactly like the French census data, and then feed this into our pipeline. So basically all of this code here stays constant. And this is what we did, and it worked actually quite well. So for instance, for all the home locations and the work locations and so on, we could use quite a lot of OpenStreetMap data, for instance. And then we set up this whole process, which of course is not as high quality as in France, because kind of we used all this just quite coarse data, but it actually works. And we compared with the mobility service in Germany, and we have quite nice results. So now we have a synthetic population for Bavaria. And also it would be interesting now to further generalize this process and look into other countries in other regions in Germany also, to really make use of this structure that we have developed in this project with TU Munich there. The interesting thing is that already there's a couple of papers and studies that are based on this synthetic population. So for instance, we looked into surrogate modeling for agent-based simulations. We looked into a concept that's called mobility coins, where people basically trade coins to pay for their transport or gain points if they use sustainable transport, like walking or taking the bike. So there's a couple of things ongoing where we are also still involved. Which is quite interesting, because it shows that these synthetic populations are really a research tool, really enable research. And this is what is happening now in the following of that project. Okay, and with this, you have a bit of an overview of what are synthetic populations and what we are doing. At the end of the talk, I will also give a bit some steps that we are planning to do now. But let's go one step further and take the synthetic population and do a simulation with this. So what do we need on top of the synthetic population is data on the infrastructure. So we use OpenStreetMap to generate a road network. So these are all the roads, all the highways, and so on. You see them in gray here in the background. And we use GTFS data, which is basically a digital representation of all the bus lines, all the departure times. So basically the whole public transport schedule. And this is, for instance, prepared by Île-de-France Mobilité as open data. We can download this, and then we have the whole public transport network in our simulation after we convert it. So again, two open data data sources that allow us to set up a fully open transport simulation. And what you see here is an example for Lyon. So in gray, you see all the cars moving in the road network. In blue, this is when somebody starts a work activity in the morning. And then in black, you have all the metro vehicles and all the TER around Lyon. Okay, so how do we do this? We start with a synthetic demand. So we already know this now, the synthetic population. And then we simulate all of them in the same road network. So for instance, if there's too many people who want to use the same road at the same time, then there will be congestion. The travel times will go up. So there's a certain traffic dynamics in the simulation. And this is something that the agents, they will perceive. So they will see, okay, it took me a lot of time to do my trip. Maybe I arrived late at work. So the agents, they can make different decisions. So this person here can say, okay, there was a lot of congestion. It took me a lot of time. I didn't want to spend so much time in the car. Maybe I change my decision and I use public transport now, and maybe some little walk trip in between. So basically, all these agents, they make now decisions based on what they perceived in the transport simulation. They have a new configuration of their daily mobility plan. And then this is an updated version of our synthetic demand. Then we again do the simulation of all of them. We will have different traffic patterns, different crowding in the public transport, and so on. And basically, if we run this loop for a long time, we see how the decisions of all the agents stabilize. So what we see here is the mode share, so the percentage of trips that are done by a certain mode of transport. And there we see, okay, over the course of multiple iterations, this is something that stabilizes and in parallel, basically the congestion patterns and so on also stabilize in our simulation. So there's multiple tools to do these kind of things. We in particular use MatSim. So it's a tool or a simulation framework for transport developed by TU Berlin, ETH Zurich, and we are like one of the kind of the third big contributor, I would say, at SystemX. There's 50 plus research groups and companies worldwide that are using it. I'm involved since 2016. And basically, this is a framework that allows us to set up this loop and then, for instance, look into mode shares, traffic patterns, emissions, noise. There's many different extensions that allow you to do all of this analysis then on the transport system. And the big components here is first this traffic model. So MatSim is a mesoscopic simulation, which means basically that we don't, like it looks here in this visualization, that we kind of second by second simulate where the vehicles are on this graph links here. But basically, we represent the whole network as a directed graph. And then the agents, they kind of jump from link to link. So a bit different than what we see here in this visualization. So basically, we always have these links that are represented as a queue and a buffer. It means a vehicle arrives in the queue. In this queue, it has to wait for a certain time that it takes to go through this link in free flow conditions. For instance, 5 seconds. Then it arrives here in the buffer. So this is basically all the vehicles that theoretically already went through the link and now are waiting to go to the next link. So there's this flow capacity that defines how quickly agents go from this queue to the buffer. And then in the next time step, they may switch to the next link, but they can only do this if we don't exceed the storage capacity. So this is basically just the space. So it means that if my car is currently here, I already went through this link. Now I want to go to the next link. I can only do this if there's some space here on the downstream link. And this basically then creates traffic patterns where the vehicles, they are kind of getting stuck up. They are congesting over multiple links, and the traffic times goes down and so on. Then we take this, basically this is kind of a discrete process, but then we still can interpolate, saying basically when did the vehicle came into this link, when did the vehicle come out of this link. We interpolate these two values, and this is then how we make these smooth visualizations. But what is important here is that this is not the real thing that's going on in the simulation, but it is basically just representing what comes out of these queue dynamics. The second big component in our simulation is the decision making once we have the traffic patterns. And for this, we use something that is called a discrete choice model, or in particular, in our simulations, this is a multinomial logit model. So these models, they look like this, that we have certain choice options, for instance, using the car, using public transport. And all of these, they have a utility function. This is what we see here. A utility function consists of certain input variables. So, for instance, what does it cost me to do a certain trip by car? What will be my travel time? Or, for instance, how many transfers do I have to do if I'm in public transport? And then, basically, these are weighted with a certain beta parameter. And these are behavioral parameters. It basically means how much do I value cost when I want to know how much am I interested in this car alternative, how much do I weigh doing another transfer. So basically for each transfer, my utility will get worse because I want to choose the best utility here in this approach. So it means also if my wait time goes up, my utility will go down. If my travel time goes up, my utility goes down. So basically all of these, they have a certain influence on my choice, but they are weighted in a different way because maybe cost is more important for me than having a short travel time. Maybe I'm willing to trade these two dimensions. This is basically what is reflected in these multinomial logit models. And once I have estimated all these beta parameters here, I can do this based on survey data. I can sample these choices. So this is kind of the multinomial logit formula. We have here these individual utility alternatives, and then this gives us a probability from 0 to 1 for each alternative, and we can just sample, and this way we simulate the behavior of our agents. So setting up these models is quite a complex process. So this is now a real-world case where we have our utility function for public transport, for the car, bicycle, walking. And here, as an example, you see a bit then how these parameters look like. And this is something that involves a lot of data preparation, cleaning, and calibration. And we are working on automizing this process already for a while. So this has been going on over multiple exploratory research projects. And we are almost there that we can publish this, that we can really set up these behavioral models in a completely standardized and automatized way. But this is also something that is currently going on. And already the baseline model that we currently use is packaged in eqasim Java, which is basically the part that connects our synthetic populations that are already standardized with MatSim to run standardized agent-based simulations. This is kind of this link between these two tools, which also works well and on which we actively work. So basically for Île-de-France, everybody can run a standard simulation for the whole region. This is already something that is working. Now, what do we do with this? Let's look at some use cases. So all of these use cases are kind of integrated into Liaison, which is basically our platform that combines a bit all our different efforts in these different projects for decision support and research in transport planning. We already have a couple of interfaces, and I will show you a bit what is behind them. So for instance, from different European projects, we looked into logistics, we looked into on-demand mobility services, we looked into energy, electric vehicle charging, energy demand over the territory, and also at logistics demand for the city of Copenhagen. And we can have a bit a look at these different examples, but basically all of this is integrated into this scope of Liaison at SystemX. So one big topic that we are working on is on-demand mobility. Basically, this means that we have a fleet of taxis or vehicles, and there are certain customers that send a request to this service. So you can imagine this as Uber, and a lot of people, they project this with autonomous vehicles in the future, that there will just be these shuttles driving around and then bringing people from A to B. But these services already exist today in certain rural regions for mobility, reduced people, and so on. And here you see a visualization of this. So we have this fleet driving around here. These are all these taxis in blue. This is for Zurich here. And then they pick up at these blue bubbles some customer, and then they drop them off in red. And what is behind there is an assignment problem. Because if we have our whole fleet here, these vehicles, they have a certain schedule. Let's say in this example, we have vehicle A that is already picking up request 1, then going to this stop here to drop it off. And then there's vehicle B that will go here to pick up request 2, pick up request 3. So we will have 2 on board of this vehicle, and then one by one, the vehicle will drop them off. And the big question is now, if there's a 4th request arriving here, going from this place to that place, where should I integrate the pickup and the drop-off of this request, either here in the schedule of vehicle A or in the schedule of vehicle B? Or I could even decide to reject this request. And this is basically a big assignment problem, and our simulations really help to work on these algorithms behind this. So we work a lot on designing these algorithms, and depending on what I do, I have different outcomes. So for instance, here I have a certain fleet size for this simulation, and then I look at different fleet assignment strategies. So for instance, the orange one here is a global bipartite matching, which will always try to minimize the empty distance of the fleet. This is actually what we see here on this axis. So how many kilometers are driven without a customer, because I just dropped somebody up and then I'm going to the next one. And there I see here that in terms of this empty distance, this orange one is the best, because this is really the objective of this dispatcher. And for instance, the green one is kind of one that will redistribute these vehicles continuously in the network. So you will try that in any corner of the network, you always have the same probability to find a vehicle. So there's constantly moving around these vehicles, which will make more people have access to this fleet in an easy way. But on the other hand, it drives up the empty distance, which is a cost for the operator. And there you see already what different decisions we can make when we design these algorithms, and our simulations help to actually look into this. We can combine this then with a whole simulation procedure. So let's say we have our simulation. We can then calculate, for instance, wait times. So how much in each place of the network are people supposed to wait for a vehicle? Because it depends on the availability. And we can also estimate what is the distance, what is the empty distance of the fleet. And we can put this into a cost model for the operator and calculate, for instance, what is the cost, the fare per trip or per kilometer. And these two things, the wait time and the fare, they can go into a discrete choice model again, where the agents, they will make their decisions. And so if the wait times are too high, the agents don't want to use the service. And then this goes again into our simulation. So we really get into equilibrium between the wait times, the costs, the fleet size, and so on. And what we then see here is these kind of graphs where we have a certain fleet size where we attract the most requests possible. Then if we go down with our fleet size, it means that our service is not so reliable anymore. What we see here then is the same equilibrium point for the wait time. So the wait time is quite high. This is why not so many people want to use it anymore. But if I go really up with my fleet size, the costs here, the distance fare will go up because we need to pay for all these vehicles, for the maintenance of this fleet, for the fuel and so on. So again, the demand will go down. So there's a certain sweet spot for the demand here. But what is important is that each of these points is an equilibrium point, meaning that if we have a small fleet, we can say, okay, there's a certain wait time involved. Maybe it takes a bit longer for this service to come, but it is quite cheap. So this is kind of a service that is accessible to everybody. Or I have quite a large fleet size, which costs a lot to use, but it is quite quick. So this is a premium service. And what we see in this simulation is that both the accessible service and the premium service would be feasible for this example of Zurich, for instance. So the city now could decide, even if there are no autonomous taxis yet, what would be the case that they would prefer, and maybe already design their policy and regulation in this direction. This is kind of the value of these really forward-looking long-term simulations. We did the same thing for Paris. So there we find out, for instance, that the most demand could be reached if we deployed 25,000 taxis. So, and this would be then at the price, for instance, here of 30 cents per kilometer. And now we can all ask the question, is it realistic that one day we will have 25,000 taxis in Paris driving around autonomous? Maybe not, but kind of these simulations, they give us a magnitude, they give us an idea of what we could expect, and now we could decide, is this something that we want, and then deploy respective policies. We look at different things in on-demand mobility. For instance, here's a RER arriving in a town, and then we have in blue these individual cars or the shuttles that will bring the people to their final destination. So this is first last mile services that we have been studying. We have been looking at the Grand Paris Express. So for instance, for most of the stations nowadays, we don't know exactly how they will be connected with buses to the surroundings. So one idea is always to use on-demand mobility services. So we looked, for instance, at how this could be designed for Saclay, to basically deploy these individual shuttle services instead of a bus line, and then we can compare which one is the most efficient one. One topic that we have been working on. In on-demand mobility, especially Tarek is working on fairness. So what we see is that most of these algorithms, they reject requests of people who take longer to enter the vehicle with a higher probability, like for instance, wheelchair people. So can we fix this inside of these algorithms? And there we have something that's called a CCAM designer. So this is already a tool on the liaison platform that you can use, and then basically click and find, configure your own kind of service, and then look for different use cases. For instance, this here is in the UK, in West Midlands. How can I deploy this service? You can then plot how the vehicles are moving for this deployment case of an on-demand mobility service. So this is kind of tools that is already online that we provide. We have been looking at charging infrastructure. So where to put different chargers in the network so most of the people have access to this. This is something that we looked at with Volkswagen, and then also with Paris-Saclay. There's another interface which is more interesting for the people at SystemX, or for the external people, contact us if you're interested to see a demo of this, where we can basically look into different deployment of charging infrastructure across the territory in Ile-de-France, where we see all the different mobility flows. So this is really an interactive interface. We had a recent project with the Ville de Paris where we looked at the zone trafic limité in the center of Paris, where you can only go through with the car now if you are actually doing an activity here. So this is something we can test quite easily with our models. What was interesting for them is especially this fine-grained analysis. So for instance, we could check for each hour of the day among the residents, among the visitors, what are their socio-professional categories, what are they doing there and why, and who is impacted in which way by this policy. So for instance, here we see now how the flows change if we forbid people to directly use the car to go, for instance, here on the Boulevard Sébastopol. And we see that these people, they need to do detours. This is all these red lines here. So we also see, for instance, where would the traffic move, or where is the traffic moving now that this policy is in place. And this is something, for instance, that was really interesting for the Ville de Paris. We also looked into logistics. For instance, for Lyon, we took our synthetic population and then generated all the packages that are delivered by DHL, Chronopost, and so on. And then we simulated this. So there is also quite a bit of things going on for logistics, and a similar thing we also did for the city of Copenhagen. And there's many other use cases in the community that we will not look into detail now, but you will also find them in the slides here. So the final question is, are we replicable? When we generate synthetic populations, yes. For our simulations, we are close. We are working on these behavioral models, but soon we will be fully replicable here. And in our use cases now, we need to apply all of these methods so that in our papers and so on, everything is completely reproducible. So we are close, but we are not exactly there yet. So there are still things to do, especially for eqasim. We want to apply this to other geographical contexts. We want to modularize the framework to replace the simple approaches that you saw also by machine learning, deep learning approaches. We can also make use of LLMs to improve these approaches. So this is something that is going on. And then, of course, we want to go beyond transport. So these synthetic populations can be used for energy systems, for health systems. During COVID, this was used quite a lot, climate change adaptation. So if you have use cases in mind where this can be used and you see everything is open and easily usable, then let's discuss. And that's it from my side. So I hope this was interesting. I didn't go too much into detail into all the methods, but I hope this was a good overview of all these things that we do with the synthetic populations and with the agent-based transport simulations. Okay, so
thank you very much, Sebastian,
and,
for this.
If you have questions, we can do this now.
Thank you for this rich talk. Yeah, we have time for questions. Jan, please. Yeah. I don't see if Jan, you raised up your hand to talk. Or...
No, sorry.
Okay.
Pardon, j'ai fait une mauvaise manipulation.
No problem. Yeah, maybe I can start. Thank you very much, Sebastian. Very interesting. Actually, my question, one of these questions is related to the machine learning part, and you already mentioned that in your previous slide, I think. Which kind of connection you see? The question has is, for example, probably to train your multinomial logit model. Is that one of the things you have in mind to integrate a kind of machine learning in this pipeline, or not necessarily?
Not in particular. I think for the multinomial logit model, this is quite standardized. So I think for the time being we will stay there. But I can.
I mean, actually, when you calibrate these, what you calibrate the model parameters, it is in some sense a training. I guess you use that by kind of Newton-Raphson, or I don't know which.
Yeah, we could do this. I think for the multinomial logit model, I will just go a bit further here in this presentation. In the multinomial logit model, the big advantage is that it's really interpretable. So all these beta parameters, they have a certain meaning. They are, for instance, in minutes, utility per minutes. And this is really important for the economists that work with these models. So probably for a while we will stay with this. For our simulations, we could use some black box machine learning algorithm and then simulate these choices. But there's always this aspect that people want to interpret these parameters. So in this case, we will rather stay on the standard multinomial logit model. But where the machine learning is important is, for instance, for the generation of the people, of the persons. So for instance, there's people who use Bayesian networks, where you basically have an age distribution, and then dependent on your age distribution, you sample your gender, then you sample whether the person has a car, and so on. So there you have at one point the structured learning, and then you learn the distributions. There's approaches where people use variational autoencoders. Basically, you have all the attributes of a person in the input. Then you kind of learn a certain compressed representation with a mean and a standard deviation. And then you decode this to get back to the same person. And then you can use this decoder to basically just sample new persons here. This is one approach. Or then there's also people who use GANs. So basically, you have your generator that generates persons. You have your real data, and then you have your discriminator in the GAN approach that basically says, does this now come from my generator, or does it come from the real data? And then basically, once this discriminator cannot decide anymore, is it the generated person or is it the real person, then basically your generator works well, and you can use this to generate people. And this is, for instance, ongoing approaches, and the same thing. And this is even much more research kind of starting research then for the persons is basically for the activity chains that you say, okay, for instance, you could take each of these activity chains here as a picture, and then you use a VAE, you use a gun, you use some diffusion model to try to generate these activity chains for the people. And this is really a starting research topic. There's actually not a lot on this so far, basically how to generate these activity sequences. Yeah.
Thank you. I see there is a question from Abdelhadi. In slide 20, can you elaborate more on how the activity chain is defined? Is it provided in the data source, or it is something that you design in slide 20?
Well, I'm on a different presentation now, but it's the same. Same content.
I think he's talking about the main slide presentation.
Yeah, but it's the same slide here. I mean, wait, then I quickly change again.
Yeah, take your time.
Should be quick. Slide 20. Yeah, okay. So, so the question is, how is it defined?
Can you elaborate more on how the activity chain is defined? Is it something provided in the data source, or you design?
Well, in the data source, in the survey, this is exactly structured like our synthetic population. So we have this table here with, well, basically in the service, these are trips, which is kind of the inverse. So here we see the activity with a start time and an end time. Actually, in the raw data, in the survey data, we have trips. So basically, a trip that starts at a certain time, and you have a home activity before. So basically, we are between two lines here. So a trip will, for instance, start at 8 and then finish at 9, and has a start activity type and a destination activity type. So this is basically how the raw data is structured. Don't know if this answers the question.
Yes, thank you. I think yes.
Thank you.
Yeah. Other questions from the audience? I also had another question, Sebastian, about if you understand well now, you simulate, you establish a pipeline, for example, in Paris, and you try to make it adapted for California, but for example, in Europe, or at least in France, is it possible to talk about some way of collaboration in the simulation process? Would it be possible, for example, to imagine a kind of collaboration between the simulation process that is designed for Lyon and the one that is supposed to be designed for Paris? So we could imagine that there is kind of similarities.
Well, for instance, for like Paris and Lyon, this is exactly the same code. It's exactly the same data.
Okay.
It's just yeah. So this is basically so eqasim on the website. We really positioned this as eqasim France now. So if we go on the website here, we have these use cases, and we have the use case France, and then basically on GitHub we have this repository here. And then this explains how to generate synthetic populations for any region in France. Generating a whole population for the whole country of France, we already did this. Actually, Tarek did this. But it's just a huge data set. So you will have, like, the population will be multiple. I think for Ile-de-France, we are in total like a 2-3 gigabytes, and then you go to the whole France. So this is gonna be much more. Of course, takes much more time to simulate and everything. But in principle, this is possible. And yeah, with Bavaria now, Bavaria, the repository for Bavaria is now a full branch or fork of the France one. So basically, if we make updates in the France one, we can just do a merge into this repository, and we kind of merge all the new features.
I understand. And my question has a dimension related to the calibration of your model parameters. For example, the logit model, when you adjust your beta, imagine if it is supposed something to serve for two different cities, and maybe we could also be able to imagine. Okay, I did some work with people from Lyon and Gustave Eiffel, but it was on prediction and we designed a kind of federated learning. So we are not at all in simulation, but that's
yes.
My question will relate more on the maybe the prediction, the learning stuff. But,
this is interesting. So basically, this automated pipeline. Well, I have slides on this, but it would be too long now. It basically it takes the raw survey data and then prepares everything to estimate the choice model and the logic parameters. And basically, we can put any survey in there. So you can take the survey for Lyon or for Paris, and then it's doing the same pipeline, and it will estimate the model.
Okay.
So, and we are there that this kind of works. And there's multiple other components. So there's something that's called MobiServe, which is also a Git project from LVMT, Gustave Eiffel, where they take all the surveys that exist in France, and basically it's a tool to standardize them. So you put it in, and then you always get a formatted survey, always in the same format. So basically, this is now really easy, so we can always run the same pipeline. This is quite nice. And now we have two options. So either we now run the same pipeline for every city in France where we have a survey, and then we can just compare the choice models, the beta parameters. Or we could even pool all the surveys and then estimate a joint model and see what this gives. We could even add like dummy variables in the logic model per survey. And then if we see that these dummy variables are not significant, we could say we kind of found the universal model of the behavior in France. And this could be quite interesting, but we're still 1 or 2 steps away from this.
Excellent. Thank you. Any other question, please? Don't hesitate. See in the chat, I don't see a question. Okay, so thank you very much. But maybe a final one. If I understand well, everything is open source, which is actually great. I think it is open source. So yeah, very, very interesting. Very good for the community. I don't see any additional question on the chat. So thank you again very much, Sebastian, for this excellent talk. And thank you all for your presence. Yeah, and see you soon in the next seminar.
Thank
you. Have a good day.
Bye.
Bye.